All right, let's go over a subject called application lifecycle management. By the application, we mean a software application that's being created. Lifecycle means beginning to end, what happens. Management, running that. There's some basic sequences to how to make a software application. You can kind of imagine you're going to want to gather requirements. What does the thing need to do, right? You're actually going to design the architecture of it, like what are the specific pieces and parts and how are they arranged. Then you can actually develop the software application. Then you're going to test it and make sure it's 100% bug-free or close enough to ship it. Then you're actually going to deploy it. It's going to get sent out or sent to people or installed on the internet or wherever it's going to go. And then you're going to maintain it over time. Now, with certain variations, this is a basic life cycle of an application. Application lifecycle management is a set of procedures and tools to manage that process. Very often you'll find software that is designed to help do this. So the software to help you manage the process of making software. Application lifecycle management. It goes by a few different terms, but essentially that's what it covers. Let's talk about data types. Data is just data. It's information. However, it's optimized for certain usages. For example, there's data that represent quantities. It could be looked at as 5.47. There's an example, right? This is a type of data. What can you do with this? Well, you can do add, subtract, multiply, divide. You do all those sorts of things, right? There's another type of data that could be Bob. Well, that type of data is optimized for doing things like concatenate. That's a fancy word meaning stick together. You could take Bob and concatenate it, add it together with Smith. Or you could do things like make it bold, or you could do things like underline it. These are all the things you could do to something like this type of data. So a data type is simply data whose format and qualities are defined, and the things that you can do with them are defined. The ones that you're used to are things like, we just showed you, things like an integer, a float, floating point numbers, a string, it's a collection of characters, these sorts of things. A Boolean, that's a true or false data type. These and others like them are very often built in to different programming languages and computer environments. They're also called native types. But you can make your own types of data. We do it all the time. We talked about dictionaries. Well, let's jump a little bit. You have user-defined data types. Well, guess what? A class is a user-defined data type. We talked about a class called a car class, or we went a little bit higher level and called it a vehicle class. This is a user-defined data type. It has properties and it has behavior. Well, look over here. We have properties. Properties of an integer would be its magnitude, its sign, plus or minus. Behavior would be add, subtract, multiply, divide. There would be qualities to a string. Length, font could be. And there's things you can do with it. Concatenate. These are properties and behavior. But these are defined by whoever made your software programming language or your computer. These are defined by you, user-defined. But it's still just data that has certain properties and certain behavior. You've made your own data types. Now, if you look at the idea of a dictionary, remember, is a key value pair. Well, what type of data is in each of these? This could very often be a string, but this value could be an integer. Let's look. Wouldn't age as the key and an integer, 46, make sense? You're using these primitive or native types to create another type of data, a pair, specifically a text integer pair in a dictionary. And a dictionary is a data type. A dictionary is a description of key value, so on and so forth, of a data structure that's composed this way. And it has properties, i.e., what are the keys and what are the values, and it has behavior. You could remove a value, you could add a value, you can remove a key, you can add a key. Data types are as simple or as complex as you want to make them, but remember, they're defined by humans. The only thing down inside the computer is ones and zeros, but you can arrange those ones and zeros in ways that mean, oh, an integer, oh, a text value, oh, a dictionary key value pair. At the end of the day, it's all data, and it's structured the way you want it to, and it's got behaviors the way you want it to. You define all of these things, and you'll do that a lot as a software developer. All right, what is a stack? In computing, a stack is all the parts you need to do something. Let's look at an example. Let's say what you want to do is host a web site. Well, you're going to need something. You're going to need physical hardware, an actual computer, right? And down inside there is a central processing unit. Also in there is memory. On top of that, you're going to need software. Specifically, you'll need a piece of software that can host the website. Down in memory, you'll have the different files, .html, these different pages that get served up. And on top of this hardware, you're also going to need an operating system. We've covered this before, but the operating system is a set of software that handles all the basic things you're going to need a computer to do. Things like input, output, data storage, etc. It's the software that sits right on top of the physical hardware and makes it so every other piece of software, like some web hosting software or like a word processor, can interact with this CPU and the memory. So, now that you have this system, you have a software to host your web pages, you have the operating system, the software sitting on top of the hardware, you have the hardware itself, and you need a language to make your website dynamic. Remember, if it's all HTML, then it's static and nothing changes. You need another language to add dynamic functionality, like it can interact with a database. It can present different information based on who the user is, that sort of thing. If you have a language to make your site dynamic, a web hosting software that can respond to requests for certain pages, get those pages, and send them off to whoever asked for them. And if you have an operating system to sit on top of your hardware, and if you have an actual piece of hardware, you have everything you need to host websites. You have a stack. So, let's give this some actual names. First of all, The operating system. The operating system that's in use in almost half of the websites in the world, it's the part that sits right on top of the hardware, is Linux. This operating system was developed about 20 years ago, 25 years ago, and it's freely available. You don't have to pay for it. Then you have a web server. That's this piece of software installed on the computer that responds to the requests for web pages and delivers the request. Again, used in about 50% of the websites in the world. Apache is the name of a piece of software. Again, it's free, and it's a web serving software. Handles requests and delivery of web pages. Now, you also need a place to store extra data. That's your database software. In this case, one of the most popular in the world is called MySQL. My Structured Query Language. Again, it's free. And then you need a language to write your code in to make your websites dynamic and interact with the database. The language is called PHP. That means Pre-Processing Hypertext Processor. Don't get into it. It's a very, very wild definition. It's a language to help you interact with databases. LAMP, LAMP. It's called the LAMP stack. It contains everything you need to host and serve up web pages, to host websites. Linux, Apache, MySQL, PHP, LAMP stack. It's just a slang term now, and that's what they mean. Are you able to develop on the LAMP stack? Means can you work with this system of a Linux operating system, an Apache web server, a MySQL database, and PHP to write your code? That's a stack. Now, that applies to websites. There's other stacks, but the central concept is you have everything you need to be able to do that operation. By the way, over on the Windows side of things, the operating system, Windows, not free. The web server, Internet Information Services, IIS, not free. The database language or system, SQL Server, not free. The language for adding rich functionality to your websites, well, there's a lot of them. It could be PHP or JavaScript or Python, a few different things you can do. That's a stack. Windows is the operating system, Internet Information Services as the web server, SQL Server is the database management system, and any one of a variety of languages to interact with your database and make your web pages dynamic rather than static. There's another stack. All right, here's a really big question. Why are there different programming languages? It just has to do with what they're intended to do. I'll give you an example. By the way, this symbol right here stands for database. Physically, it's meant to represent a bunch of hard disks all stacked up on top of each other. Because databases needed lots of storage, and the physical machines to hold them looked roughly like this. So this symbol has come to mean database. And a lowercase d, uppercase b also can mean database. Good. So here's the thing about databases. Is you have a giant collection of data. It's sometimes billions or trillions of individual pieces of data inside this. And here you are, you're the user, and you have questions about the data. Let's say you want to find all clients with accounts receivable greater than $5,000. you need to execute what's called a query against this data. You need a way to say, go to this giant mess of data and get me the name and address and phone number, and as a business name, and contact person for everybody who owes us greater than 5K. How are you going to do that? You're going to have a specific language, a computer language, that is optimized for dealing with large pieces of data like this. Large collections of data. That language is called SQL. SQL means structured query language. And it is a language that looks almost like English. And when you write the commands on it and execute them against this big collection of data, it returns the subset of that data that you wanted. In this case, the business name, address, phone number, and contact person for clients that owe you more than $5,000. So, this language, SQL, is fantastic for querying large amounts of data. It's horrible for displaying things on a web page, or for making web pages, or for handling images. It's purpose-built for this exact situation. Large collection of data that you need to do queries against to return a subset of that data that matches certain criteria. So, HTML, on the other hand, hypertext markup language. This is the language you use to make web pages. This language, which again reads almost like English, was created, optimized for this activity of creating hypertext documents that can link to other hypertext documents. So that's why all these different languages. And there's many other reasons why one slight variation on a language developed relative to another language that's very, very similar. And a lot of the times it's not something you really need to get into as a developer, is what's better, what's worse, and such. What you need to know is there are certain types of languages where there's many available choices, and you want to be comfortable in working with one or two or three in each of those categories. So what kind of categories are there? Well, there's things like scripting. Let's cover scripting right now. A script is basically a series of steps to be done in order. Think of it as a movie script. It goes from beginning to end, and everything happens in that order. What this is meant to do is to automate manual tasks. Let's say you had a situation where in a certain file on your computer, your customer service representatives every single day could add new orders to different clients. And it would have a client 1, and then what the products were they ordered, and client 2, the products they ordered, and such. And then you needed, every day, to get a print off of that made. It would go through and summarize how many of various items. Let's say there's a red bike, and there's a blue bike, and there's a green one. You want to know how many of each got ordered. You don't want to have to open this up manually and count through all the different instances in this file and add it up. Instead, you could write a series of program steps that do that exact thing. They actually keep track of how many red, how many blue, how many green, and then they print this out on a printer for you automatically. That would be a script. There's many, 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 many other reasons for a script, and you'll get into them as you learn to program computers and make software. But the point is, you're going to need a scripting language. You'll need it for a lot of different reasons. And there's a lot of them. I'm not going to give you all the names of them right now because a lot of you misunderstood words. But we talked about why all these different languages and the categories. You'd need to know 1 or 2 or 3 good scripting language. And you would need to know HTML. It's a markup language for making web pages. There aren't a lot of variations on that. That one has pretty much got market dominance. You would need to know a good object-oriented language, capable of making very, very strong line of business applications. What's in line of business application, LOB? That is a purpose-built piece of software that helps a company in whatever their line of business is. I made up some little thing here about bicycles. If you're a bicycle manufacturer and you need a piece of software that helps manage your entire business from materials acquisition to manufacturing to storage to delivery to customer service, all of it tailored to the exact type of activity you're involved in, you might not find a piece of software off the shelf that you can buy from someone that meets the qualifications. You might have to get that built. That's a line of business application. So, and by the way, there's lots of other reasons for object-oriented programming languages, but you'll need a very powerful one used in making business class applications. And there's many other examples, but the point is that there's hundreds of languages to choose from in some of these areas. You're only going to need a couple and be comfortable and adept at a couple. And then if you need to learn a new one, it works really easily. You can learn it very easily because of your fundamental knowledge you're going to gain on the program. Different types of programs. You may hear things called a console application or a browser-based application. Really, what they're really talking about is the user interface. They're talking about input and output and how it happens. And to really fully get how this evolved and why they even care about different types, you got to go back in time a little bit to where you had a very big computer called a mainframe. Covered this briefly on your first course. Now, there was no user interface on a mainframe. What you had was a terminal, which was a tiny input-output device connected by wires to the mainframe. Really what this was usually an all-in-one unit with a monitor, a screen of some sort, and a keyboard down below. This is where you could enter in instructions and get back results for display. You enter in the sales figures for all of August 1967, and you get back a summary by product. So many red bicycles, so many green, and so many blue. But it's done at this tiny little terminal, and it's displayed on this little screen that can only show text. So that would, if you're going to make a piece of software to do this thing I just talked about, that's a terminal app. A terminal application. Good. So now we evolve a little bit. And now we evolve to the point where you have an individual house or an individual company. And in there is a guy who has his own personal computer. And on that computer, down here you have the central processing unit, and you have memory, and then you have, separately, you have a display. Well, you can install software on here that's going to, all within the confines of this little system, work for you. You've got a keyboard that you can enter data into the computer, and it'll make data appear on the display, and it's all in the self-contained little system. This display is also called the console. Hence, that would be a console application. The input-output and the data transfer and the whole operation is all self-contained in this little unit. And then they evolved a little bit. And they went, you know what? Here's our software we want people to do. Let's say it's for word processing. We're going to install it on a really big computer, really powerful. It's got a massive central processing unit that's really, really fast. It's got lots of memory. And we install our software on here. And we call that the server. And what it can actually do, because it's got so much memory and such a powerful central processing unit, is it can actually have many different versions of this word processor operating once. And not even really versions, because that implies a history and each one's different. What they are is instances. It's as if each one of these is its own word processor program, all by itself, totally isolated from any other one of the word processor program it's running. It's actually an instance of that word processing program. Why would you want that? because you can have all of your money go into this really, really powerful computer called a server. And then at somebody's desk over here, you have a pretty lightweight little personal computer that can actually, if the guy has his, here's his keyboard and such, and here's his little personal computer, it's called a tower, right? Here's his whole system. He wants to use a word processor. He doesn't have to install that on his computer right here. He just has to connect through wires into this computer right here and ask to run the word processor. And it'll do what's called, this is slang, it'll spin up a word processor instance. And it's sitting there. And he can use it. And data goes back and forth as he types on the computer. The data goes to here, and then it comes back to show what to display as he's typing in. But you're using the processing power of this really powerful computer to handle all the heavy lifting, if you will, of getting this all to work. This computer is called a client of this computer right here called the server. So that kind of application, that kind of software application is a client-server application. It's designed by a software developer in a different manner than the one before. It was all going to be in this self-contained console sort of setup. So that's a client-server application. By the way, that server is called an application server because it serves up applications as opposed to a web server that serves up web pages. And finally, you would have this thing called a browser-based application. And the terminology on this is relatively loose because it's a pretty recent development. But essentially what you have is you've got some big computer somewhere called an application server, even a web server. Either one, it's a big central processing unit or dozens of central processing units and lots of memory, right? And a piece of software on there that can serve up applications or serve up web pages. And here you are, and you're somewhere far removed from that, and you have a browser. Like Chrome, or Internet Explorer if you're forced to use it, or Opera, or Firefox. A lot of browsers. Remember, a browser is just what lets you browse the internet. Browse the web page, browse the web. So, a browser-based application would have most of the actual software would be down here on this server, hundreds of thousands of miles from where you are. The only element that you would actually use is your browser, is something that's capable of displaying HTML pages. The logic of how to handle different bits of data would all be over here on the application server. The database to store data would all be over here on this server. Essentially, it looks like that whole client-server arrangement, and it's very similar, except that the only type of program you need to be able to get this done is a browser. Where before, the client-server application, there might have to be a very small word processing, say, they would call it a they call it a shell. We would have a word processing shell, which is this tiny program that lets you connect over to the application server and do all you needed to. And that had to be purpose-built by whoever made the word processing program. You, if it was your job back then. Here you don't need that. The people who are making the applications that go on this web server know how a browser works. And they can just assume all the functionality there is going to work the way it's supposed to and just concentrate on building this back end and building the user interface, just the part that's seen to display in the browser. That user interface, of course, is made in HTML and a couple of the languages to make it dynamic instead of static. So there's like the evolution, roughly, of the different types of applications categorized by really how does the input-output happen and how does connecting to where the software itself is happen. You'll hear about a concept of what's called a high-level language and a low-level language. Of course, they're referring to programming languages. And here's what they mean. The basic evolution of how programming languages happened. At the beginning, back in the day, you had to program a computer with ones and zeros. Again, back to those cards where they had holes punched And typically the hole being punched would represent a 1. If it wasn't punched, it would represent a 0. Okay. You literally have to make your instructions to the computer, one after the other, in these predetermined arrangements of 1s and 0s that meant something to the central processing unit. That was binary code, also called machine code. That's what the machine can understand. At its most fundamental basis is the 1s and the 0s. But that's not very easy to work with for a developer. So almost immediately, they created a little piece of software called an assembler. And they could put this on a central processing unit, programmed into memory, and it meant that you could actually take code that almost resembled English, like move and add and subtract. And you could do those instructions. Now, they got broken down by the assembler down to 1s and 0s so that the actual CPU could run them, because the CPU can't operate off of MOV and ADD. It operates off of 1s and 0s, and that's all. It had to literally be translated to the plus 5 volts or 0 in every instance for it to work. But you could have software that let the computer programmer write in almost English and convert it down into 1s and 0s. That was the first generation language. Well, it's gotten progressively easier and more difficult over time. And here's what I mean is, we're dealing now with what is generally agreed upon as 4th generation languages. And these are things like C# that you're going to learn, Java. These are 4th generation languages. And the thing about them is they read almost like English. When you're reading these things, you can generally surmise what the code is doing simply by reading through it. Whereas, unless you've done it a lot, you can't surmise what those 1s and 0s are doing just by glancing at them. Also, it would take about, 50 to 100 of these 1s and 0s just to do A plus B inside a computer. It'd be 5 plus 7. It would take a bunch of these instructions to get that command to execute. So these 4th generation languages make the development of software a lot easier because, for the most part, you can read them like English. And what they do is they combine long series of commands into 1 or 2 statements that can be executed by the software developer. Now, the trade-off is the people making the language decided how to implement what they did. And sometimes you like the way they did it, and sometimes you don't, but you're, for the most part, stuck with it based on what language you're using, which is another reason why there's variations of different types of languages, because of the fine details under the hood of exactly how the developers of the language decided to implement things, and you get to choose languages that are more or worse, better or worse for your chosen use. So that's high-level and low-level languages. Compiled languages versus interpreted languages. So a compiled language is designed to have you write code, one statement after the other, in a language that you can read. It's a 3rd or 4th generation language. And then the compiler is a special piece of software that can translate that down to the 1s and 0s that the central processing unit can understand. You can think of a source for the higher generation code and a target for what language, typically machine code, you want to convert it to or compile it to. This is why, very often, the code you're writing on is called source code. Because it's the nearly English, readable by humans code that's going to get compiled or converted down to the target language. That's compiled code. Now, here's how that works. You write every instruction, one after the other, and when you're done and you want to run the program, this compiler first goes through and converts every single statement down into its comparable statements in machine code. Thousands and hundreds of thousands of them. Only then can the program run. And you can execute it and use it. Okay? Now let's look at interpreted code. Interpreted code is where you take your instructions, instruction 1, 2, 3, 4, 5, and you write them. And you have a special piece of software called an interpreter that takes the first instruction and converts it down to machine code and executes it. Then takes the second one and executes it, and the third one and executes it. It's interpreting one thing at a time and converting it down to something the computer can use. Now that's a very simplified description, but you can see the central difference between compiled, where you have to take all of your source code and convert it down into machine code, and then you can execute, or interpreted, where you can take one instruction after the other and one at a time convert it into machine code and execute that instruction. Okay, we're going to talk about how to use scripting languages in your website. And this is going to be a very simple description. You're going to learn everything about how to do this in detail on your course. Remember that what you have in a web page, an individual page, is code written in HTML. And while you haven't yet coded in this, there were examples in your very first course. It's pretty basic. You have these things called tags. They're at the beginning and end of the document. And then in between, you would have text that says, this is all about, and then you'd have a tag called bold ninjas. And then you'd have end bold. The tag is compared to two parts, the bold and the end bold. This tag of HTML is composed of begin HTML and end HTML. And you have, guess what, an interpreter that can read that pair and figure out what to do with it. And then read this pair and figure out what to do with it. One after the other, and it'll make your page appear, and guess what, all of a sudden, ninjas is bold, because that tag said to make it bold. So there's the basics of an HTML page. Again, you're going to make a lot of these on your course, and you'll make hundreds of thousands in your career. But how do you use a scripting language? Why would you use a scripting language in that? Well, the reason is, again, that what we just described there is static. It can't change over time. What if you actually wanted to have on your screen, it would say, this is about ninjas, that's bolded right there. Okay? But you could then say calendar of ninja events. And right up here would appear that month's calendar. I'm recording this in February, so February's calendar would pop up. But when someone comes back to the website several months down the line, you want it to say June's calendar and show June's events, not February's. How do you do that? You can't do it in HTML, because in HTML, you're saying exactly what it's going to say, and that's all it'll ever say. It doesn't have any, if the date happens to be blah, blah, blah. There's nothing like that in HTML. HTML is simply hypertext markup language. How do you mark up or change text? You can't create the text on your own. You have to tell it what the text is going to be and what to do with it. So, how do you do it? You do it with a scripting language. And here's how that goes down. You have your HTML and your end HTML, and you've got other things in there. You've got the text about ninjas. But then right here, this is where you want the calendar to appear, and you put code in here that's not hypertext markup language. You put code of a different type. Most commonly, you put code made in JavaScript. Now, JavaScript is cool in that you can apply if-then conditions to it. And you can do things like get data from a database and display it. It can make your website, your web pages dynamic, changing over time or based on other conditions. So how do you do it? Really simple. One of the tags available in HTML is script. And of course, end script. In here is where you put, in this case, your JavaScript code, which could basically say, go to the PC and figure out what the date is, go to the computer, figure out what the date is, and then grab a calendar graphic from a file and display it. Obviously, you'll learn how to do this with exact code. But notice that's if and then. It can make decisions. That's what JavaScript can do for you. HTML can't. So all you do is put a script tag in here, an end script, write your code, and then remember, all of this is going to get interpreted by a browser. Your Internet Explorer or Chrome or Firefox, it's going to go through and it is an interpreter. It's going to figure out what each of these pieces mean, and then it's going to display your web page. When it gets to this tag, it finds the end script tag, and then it grabs all this JavaScript code inside and executes it. And based on what the code says to do, it creates HTML that your browser can use. But that HTML can be different every time you visit the website. Why? Because the date will be different. And you've built your JavaScript code to check to see what the date is and literally create HTML based on a changing condition. That's how you use a script. Now you get nice and fancy, and you can actually write the script and store it somewhere else on the computer and just refer to it right here so you save space, but it's still just going to say, oh, there's a script, and it's in between these tags. I should go get the contents of that script, execute it, based on what it does, create HTML, and then use that to display my Ninja calendar. All right, you hear the word framework a lot. What's a framework? Well, in the physical world, a framework is a supporting structure. It's the frame. The frame of a house would be the thing that you can put the siding onto, you can put the roof onto, you can put a door into, you can put windows into. All of those things aren't the frame. The frame supports those things. So how does this apply to software? In software, a framework is a collection of things. It's a number of things. But what a software framework does is it lets you build software. It's a collection of things that help you build software. What are those things? Well, they are pre-made code. It's already been written for you that handles very, very common things. It's in what's called a library. You have a library of code. It could be things like documentation on how to use the framework. It could be an actual compiler that's needed to compile your code. It could be an interpreter to interpret your code. All of these things don't need to be recreated every time. So why not just package them all up into one thing, a framework, give that to a software developer, and he can use that to make software. That's what a software framework is. And they can get specialized. They can be for making console apps, or making client-server applications, or making web browser-based applications. But it's still just a collection of code libraries and documentation and compilers or interpreters that help the software developer make those types of things, those types of software applications. So one of the most common ones out there, and you'll be learning a lot about it on your course, is called ASP.NET. ASP stands for Active Server Pages. And that's actually a legacy, old school tool for making dynamic web pages. It's not very commonly used anymore. It's a pain to work with, but it is out there. ASP.NET is not active server pages. It was just a nice familiar term for making dynamic web pages that they combined with the .NET framework. Well, what's the .NET framework? This is a collection of code libraries and documentation and compilers and interpreters that you can use to make software. In this case, you use it to make web applications. That's the ASP.NET framework. But there's a thing just called the .NET framework, code libraries, documentation, compilers, and such, that's used to make almost any type of application. Client server, console, web application, you name it. You can use the .NET framework to make it. And you'll learn a lot of detail about that on your C# and .NET course. But that's all it is. It's a collection of code, documentation, compilers, and such that help you to make software. Oh, and it comes from Microsoft. One last thing. Earlier I mentioned structured query language. And in fact, we talked a little bit about databases. Show you the symbol for a database. There's a very common misconception when it comes to databases. And what it is that you have the data itself, and it's all stored somewhere in memory. And then you have special software that helps you query the data and manage it. Like, how is it arranged? Do we delete parts of it? Do we add new elements? The software to run this is a database management system software. It's not the database itself. The database is the collection of data. It's just data. A database management system is software to help you manage and query the data. It's a very important distinction. And very often, just in routine conversation, we colloquially say the name of the software when we mean the database. But it just happens. You need to know the difference yourself. Where you'll find this used, the most common players in the market are a thing called SQL Server, which I already talked about when we were talking about stacks, and MySQL. Both of these are actually database management systems. They are special software to manage and query databases. They are not databases themselves. So, when you hear someone say, I have a SQL Server database, what they really mean is there's a database that's being managed by this piece of software called SQL Server. And if they say, I have a MySQL database, that they mean it's a database, a collection of data, that they're using MySQL to query and manage. It's an important distinction. Now, how do you connect to the database? Essentially, this database, this is a physical machine. This is a central processing unit and memory and an operating system to run the actual thing. And then installed on that computer over the operating system is this software, say SQL Server or MySQL. And what a person does is they turn on the software called MySQL or SQL Server and use it. It has a nice interface. It shows you your different databases, and here's where you can type out your queries, and it'll display the results. And you're using that piece of software to, again, query and manage databases.